So we're going to we're going to solve a problem which is basically trying to figure out if in an array, if there's a value that matches an index by value. As you can see, if there's an array value, a bracket I equals to I, which is the index, then basically we can say that there's a index value match. Okay, so, and there's another constraint in this problem, that the algorithm that should run in the time of big O log base 2n. So what does this mean? It basically means that we cannot linearly search if there's a match, because the most intuitive way, the most simple way to think about it, if we were given an array of some, say, n elements, we could check each one from the first element to the last element if there's an index value match. But for this problem, that's unacceptable, and it's also asking for a more efficient algorithm to figure out the index value match. There's two crucial conditions: that the array is a sorted list of distinct integers. This basically means that it is not only sorted, but also all of the values should be distinct. So it does not allow any duplicate values within the sorted list. So it should be strictly ascending. It's not non-descending. It should be a strictly ascending array. Okay. So the problem gives an example. So to more illustrate what we're trying to find would be, we have an array which has a value of -1, -2, 3, 5, 6, and 7. So remember that in this problem, unlike a lot of programming languages, in this problem setting, the first index is 1 instead of 0. Okay? Which means that in implementing this algorithm in programming language that support starting from 0, you should add one more to the index value. Add 1 to the index value. Okay? So in this case, as we can see, the index is the second row here, and the first row is for the row. Okay, so in this case, as you can see, the third index satisfy what we're looking for, right? Because the third element of array A has a value of 3, and it's the third element, so it's A bracket 3 equal 3, which is what we want, right? So this is what we're looking for. But there, of course, as it's also illustrated here, there are cases that do not have this kind of matching, right? So basically we're trying to figure out if this array has that index value match or not. So the function will basically return in implementation 1 if there's a match, and say -1 if there's no match. Okay, so what kind of insight should we have to solve this problem? First of all, the problem said that it does not allow linear to n time complexity, and it should be log of 2. So in this case, what rings a bell? It's a binary search, right? A binary search is the algorithm that has the time complexity of O log n, which we could consider at this point. So consider binary search. But we also know that this is not a traditional binary search, but it's more of a there's a little bit of twist from the traditional binary search here, but we could adequately implement it, and we'll see why. Okay, so notice that for some x which is greater or equal to 1 and smaller than the size of the array, if a x, which is the x index value in the array, is greater than x, so this is not what we want, right? We want this, okay? Anyway, if ax is greater than x, then ay is greater than y for all y greater than x and y less or equal to the size of the array. And this is because of the condition that the array is a sorted list with distinct integers, okay? So let me give an actual example. Let's give a very straightforward example that the array A has a value of 2, 3, 4, 5, 6. Okay? So 2 is the first index value for A, right? So in the index row it could be 1, 2, 3, 4, 5, right? In this case we can see that the value of the array is always greater than the corresponding index value, right? Because when A has the value of 2, its index is 1. When A has a value of 3, its index is 2, and so on, right? And we have to notice that the index will never catch up the array value, since we already confirmed that A1 is greater than 1, which is A1 is 2 and index of that is 1, right? Since this relationship is established, index can never catch up the value in corresponding value in A, because index always increments by 1, and the array values must at least increment by 1. Because why? Because we have the sorted and distinct integer condition of the array, right? So the minimum increment, like at least A, should increment by 1. And the index by nature increments by 1. So once the value is bigger than the index, it cannot catch up. So from this, we can figure out that as we add some array, this is an example, but in a real array data, if we observe that ax is greater than x, it means that the x's, the values that are greater than x, as I said here as y, will always be greater than the corresponding y. If ax is greater than x, then y that is greater than x, ay will be always greater than y, because it can never catch up. So from here we can make a connection of this finding to the binary search, because binary search is basically given an array, divide into two subarrays, okay? Test for some condition. Based on the condition, discard half of the array, right? That's why the binary search has such superior time complexity to just simply linearly searching everything, right? So here, if we try to imitate the binary search, we can check the mid value. Let's say that's a, there's an array a sharp, okay? Here we can always we can get the mid index value and then test for if ax is greater than x, right? Because if this ax greater than x establishes, we do not have to care about the right subarray, because this will always be bigger. Ay will always bigger than y. So this means that we will never accomplish ai equal to I, right? So we don't have to care about the right subarray. We just can recursively implement this binary match function into the left subarray, right? And since it's a recursive function, then we will be able to again, I'll change the color of the pen. We'll again split this and test if here, if ax is greater than x, right? And we split it until we hit the base case, because this is a recursive function. We have the recursive step, which is basically dividing half and half and half and discarding one based on the ax greater than x condition. This is the recursive part, right? The division part. And the base case. So the base case is basically at the point that we cannot possibly divide more and more, right? When the resulting array is 1, right? But for this problem, this is not the true base case, because we're trying to figure out whether there's a match or not, right? But since this is the base case for the recursion itself, we do have to incorporate this. So then what would be the check? So if we're implementing this into an actual code, then how would we implement this? Like, in what condition should we return the value of 1, which is match? How could we implement this? Okay, so I'll write the code here. I'll erase all of these over here. So in terms of the code, it could be written as the binary match code with the argument of an array argument, I'll just write as ARR, and the leftmost index, I'll just write it as. So this is basically what I'm writing is standard. I mean, yeah, a prototype. Original twisted binary search function. The structure is the same. So if R, the right index, is greater or equal to left, which means that this array that's fed in is not empty, right? So this is at least one, okay? So when R, the rightmost index value, is greater or at least equal to the leftmost index value, it means that this array at least has size 1, right? This is the base case part here, what I talked about. But this does not guarantee that the base case will solve, because usually recursive functions are you split until it's no longer splittable, and then since the problem becomes too trivial, you can solve from there, goes up. It's it's usually how recursive functions work, but in this case it's not that, right? We're not doing a merge sort or something like that. We're just trying to figure out whether there's an index value match or not. So this can be said as the base case of the recursion itself, but it does not guarantee the correctness of our algorithm, which has the objective of figuring out the match or not, right? Okay, but we have to incorporate in the function since it's a base case, still a base case for the recursive function. Okay, so this is the part. So if this does not hold, we can just return the failure, which is -1. Okay, so to do something, this R should be greater or equal to L. That's the base case, which is at least the minimum requirement to dive into this function. Okay, so we're trying to check recursively whether the midpoint and check for this AX is greater than X condition, right? Since this leads to discarding the right subarray. If X, so we're trying to put X as mid, right? So since this is a recursive function, at first this binary match function, the L will obviously be 0, right? And R will obviously be the index for the last element in the array. But as it's recursive, L could be the middle plus 1 and R could be the end. Or if we're considering the left subarray, L will be 0 and R would be mid -1, something like that, right? So these should be fed into a parameter, and the mid index can't just be which means that the mid index can't just be the array size divided by 2, because that's just only for the original array. As it goes recursive, we will have to calculate the mid index value based on the fed in, the leftmost value L here and the rightmost value index R here. So how can we do it? It's simple, right? From L that's fed in, we add the difference between R and L, the gap between it, right? Which gives the total length of that particular array that's fed in, and divide that difference by 2, right? And add it to L. So pictorially, you're getting this amount by R minus L divided by 2 here, and then just add by L, right? So you can get the mid index, right? So this, okay, it's much easier to understand when you draw it. So, okay, since you got the middle index, now I'm going to talk about what I mentioned. How can we figure out if the return, if there's a match, which is equivalent to returning 1 for this function? It is if the array mid-index is equal to mid-index, we return 1. Makes sense, right? So, since this is a recursive function, even though us reaching the array size of 1 itself does not guarantee that the function that we will get a match, but splitting this array into the array size until the binary match gets fed in array size of 1, which is the smallest possible array to get in, will at least give us the opportunity to really figure out at last whether there's a match or not. At last, right? Of course, at some point, even much before, this could have this array mid-index equal to mid-index could be satisfied, so that's good. We already got a match. But at least when we haven't discovered it until we have to check for the array size of 1 subarray, we can at last check, right? Because if the array size is 1, then basically the value for R and value for L will be the same, right? Because for array size of 1, the leftmost index will be always same to the rightmost index, which means that the difference between them are 0, so the middle index will be no different from the leftmost index, right? So we can just check for 1, right? So this makes sense. So this can be our true base case. I don't want to put it as base case, but it could be considered as a base case when we have to split to that extent until an array of 1, but also could be satisfied before, okay? So, and then the left part is pretty straightforward. So now we're going to utilize this part, the AX greater than X part. We already know that if AX is greater than X, then we have to discard the right subarray because there's no clue, there's no way that we will find a condition match of AI equal to I in the right subarray part, because our sorted list of distinct integers assumption for a condition for this given condition for this array, right? So we already checked for the middle index. So if array middle index is greater than middle index. Yes, but one thing to note here is that basically most of the programming languages, like not R or those programming languages, but usually the array starts from 0, so we could add 1 to this middle index, right? Because basically, okay, here let's say that we're writing this in C, and the C index will be 0, 1, 2, 3, 4, 5, while in conceptually we're considering for this, but in implementation we're using with C, say C, so we have to think about all these indices, right? So in this case, for this match, we have to C index, mid index in C will be 2. Yeah, of course here we have to also add 1, right? So mid index plus 1. will be 3, which gives the conceptual index of 3, which makes sense with the array, right? You can see it, right? So we always will add little index value by 1, add by 1 if we are implementing in a language which the first element has the index of 0. Okay, so in this case, if this is basically what we wrote over there, ax is greater than x, right? So in this case, I'll change the color and kind of increase the space that I have for the code. So if this, we can discard the right subarray. We can recursively call the binary match considering the left subarray, because we discarded the right subarray. Okay, from the left, right, to the middle index -1. You don't have to plus or minus here as we did there, because this is in the implementation level. This is just for value matching, right? This actual implementation happens here, so we don't have to really care about those over there. Okay, so then this is recursively calling the left subarray, and if these both do not hold, then we can, call the binary match function for the right subarray here. Mid index is too messy. What I'm writing will be pasted in here. Just return binary match of array mid index +1 now, because we already checked for the mid index, right? And this, note that this mid index +1 here is different from the mid index here. This, again, the pink +1s are only for here, that we are matching for the value, right? So it has nothing to do with the pink +1 and the +1 here. This is implementation level in the black +1. Okay? So by this we will be able to correctly achieve whether it matches or not, whether there's a match of ai equals to I with O log n. And remember that it's a log of 2 base 2, obviously, because it's a binary search, right? We're dividing recursively 2 into 2 parts, so it's log base of 2 n. Okay, so this would be the running time for this function. Thank you.